Hey everybody, thought we'd go over this problem from 1992, but first just this unexpected beautiful snow came down here on February here. What day is it? February 16th? All right, let's go over this problem from 1992 here, where we've got this ball being swung in a circle like this at 6 meters per second. The ball is 0.1 kilograms. It is got a string of length 0.8 meters. And when it gets to the bottom, that ball is 0.2 meters above the floor there. And the first thing they want is determine the tension in the thread at the top of the circle. So to do that, let's first make a little free body diagram. That's going to help us. So at the top of the circle, we've got tension pulling down, and we've also got gravity. They're both pulling down there. And so what we are going to need to do is to use Newton's second law. That's the first step in all these centripetal problems. So the sum of the forces is equal to mass times the acceleration. Now, what forces do we have? Remember our rules. Anything that points towards the center is positive. So tension points towards the center and gravity points towards the center. So they're both positive forces there. And that will equal mass times the acceleration. But I'm going to go ahead and plug in, since it's going in a circle, we know that acceleration is v squared over r. All right, now let's move this force of gravity over to the other side because we're trying to solve for tension. So tension is equal to mv squared over r minus the force of gravity, and I'm also going to go ahead and substitute in mg for the force of gravity there. Now we've got it already set up to solve here. All we need to do is to plug in the appropriate numbers. So the mass there is 0.1 kilograms. The velocity is 6 meters per second. Don't forget to square it. The radius that we're talking about here is 0.8 meters. And then we're going to subtract from that the mass, which is 0.1 kilograms, and then multiply that by gravity, which is 10 meters per second squared. 6 squared is 36 times 0.1 is 3.6, then we divide that by 0.8, so we multiply by 10, so we're back to 36, and then we divide 36 by 8, which gets us to 4.5. So 4.5 newtons there is the first term. This is simply going to be 10 times 0.1 is 1 newton. So we get 4.5 newtons minus 1 newton, and that leaves us with 3.5 newtons. So the tension at the top is 3.5 newtons. Now, the next thing we're going to do is we're going to solve for the tension at the bottom, and it's going to be the same thing, from the bottom point of view. So let's pull this one in, and we're going to do the same thing that we did before. We're going to start with a free body diagram here. On the bottom, the center's up here, we've got tension up, and we've got the force of gravity down. By the way, we know that this tension's gotta be bigger than the force of gravity because the center's up here. So the force that points towards the center has to be bigger. So since this thing's 0.1 kilograms, we know the tension's gotta be greater than 1 newton because that would be its weight. So now that we've got our free body diagram, it's basically the same as the one before. We set it up, the sum of the forces equals mass times acceleration, and we'll go through this quickly because we saw it happen on the previous one. This time tension points towards the center and gravity points away from the center, and we can replace that with mv squared over r, replacing the acceleration. And then after that, we're going to add the force of gravity to the other side. So the tension will equal the force of gravity plus mv squared over r. And we already solved for these two terms on the previous page. We found that the force of gravity was 1 newton and that mv squared over r was 4.5 newtons. And so we know that this tension then has to be 5.5 newtons for the tension at the bottom of the circle there. Okay, now last part here is it says the ball reaches the top of the circle once before the thread breaks when the ball is at the lowest point in the circle there. So that's important, the lowest point in the circle. So determine the horizontal distance the ball travels before hitting the floor. So just to bring this back here, they say at the lowest point. So we're down here when we're 0.2 meters above the ground. All right, so first off, let's sort of envision this. We've got a velocity to the side. We'll call that 6 meters per second, and that's our Vx. And we've got a height here above the ground. That is our delta y, and that is 0.2 meters. Or more specifically, our delta y is negative 0.2 meters because we'll travel 0.2 meters downwards before we hit the ground there. So let's set up with our third kinematic equation, the vertical problem here. So our delta y is equal to v0y times t plus 1/2 times our vertical acceleration, which is g, times t squared. There is no initial y velocity because this is a horizontal projectile. And so now we get to solving for t, and we've done this a bunch before, where t is equal to the 2 times the square root over 10 meters per second squared. That's a negative. And next up, our time here will be equal to plugging in 2 times delta y, which is negative 0.2 meters here. And then our t is negative 10 meters per second squared. And so then lastly, our time here will equal the square root of, this will give you 0.4, and divided by 10 will be 0.04. And the square root of 0.04 is 0.2 seconds there. All right, so 0.2 seconds is our time. Now we got to plug in our x equation. So we'll use the same equation, but for x. So our delta x is equal to v0x, or we could just call it vx because it won't change, times time. But this time we won't have any x acceleration, so it simplifies down in this manner. Instead of getting rid of the left-hand term, we get rid of the right-hand term. So now we just simply plug in the numbers that we already have. We know that our x velocity is 6 meters per second. We know that our time is 0.2 seconds. And so we do 6 times 0.2, and we get a horizontal distance of 1.2 meters there.